Now I want to show you how to fill in electrons on a molecular orbital energy diagram, and we're going to use O2 as an example. The first thing we want to do is we want to put electrons on each side here for the oxygens that are not bonded together, and then what we'll do is we'll combine those electrons into the center to show what happens when the oxygens get bonded together. Alright, so let's look at oxygen first. We know it's got 8 electrons because it's got an atomic number of 8, which means it has 8 protons. So we've got 8 electrons, we'll put 2 in here, and then we'll put 2 in here, just according to the Aufbau principle. And then, obeying Hund's rule, we'll put 1 in here, 1 in here, 1 in here. That's 7 so far. So now we can put 1 in here, and that makes up our 8. Let me do a better job of that. There we go. So now we've got 8 electrons put in on that side. Let's do the same on this side. 1, 2, 3, 4, 5, 6, 7, and then 8. It doesn't matter which orbital that other electron goes into. Alright, so now we've got 8 on this side, we've got 8 on this side. That means we've got a total of 16 electrons that we want to deal with. So what I'm going to do is I'm going to fill that in, and we'll go 1, 2, 3, 4, and we're filling this in with the same rules, the Aufbau principle, starting from the bottom, moving to the top. Got energy on this side over here. So that's 4, 5, 6, 7, 8, 9, and 10. Now here we use Hund's rule and we put 1 electron in here, 1 electron in here, that's 12, 13, and then 14. We've still got 2 more to put in. That's 15 and 16 up there. Alright, so now what you can see is we've got our molecular orbital diagram filled in, and as you'd expect, you can see that the 1s's don't combine. You see you've got the 1s here and the 1s here, and we've got 2 in the anti-bonding and 2 in the bonding. And what that just tells us is that the 1s orbitals don't bond, and that's what we expect. And the reason is because that's the inner electrons of oxygen. The inner electrons aren't expected to bond. All the bonding we expect to see will be in the valence electrons, and you can see those are the ones up here. Alright, so let's take a look at how we calculate bond order. And the equation I showed you earlier was bonding electrons minus anti-bonding divided by 2. So what this is going to tell us is how many bonds we expect to see between oxygen. I know I've only put 1 here, but we'll see in a second that there's not really just 1 bond between the 2 oxygens. So here's what we do. We have to calculate how many bonding electrons there are. Now the way we do that is any orbital that doesn't have a star on it is considered to be a bonding orbital. Anything that has a star on it is considered to be anti-bonding. So these don't have stars. This one, so there's 2 electrons there. There's 2 electrons there, that's a total of 4. We've got 2 electrons here, that's 6. 2 here, that's 8, and 2 here, that's 10. So we have a total of 10 electrons that are in bonding orbitals. In the anti-bonding, we've got 2, and 2 is 4, and 2 is 6. Ten minus 6 divided by 2 equals 2. Alright, so that's what we expect to see in oxygen is a double bond, or 2 bonds between the oxygens. And that's exactly what we would expect to see. If we take the Lewis structure of oxygen, we've got 12 valence electrons in total. Now, not total electrons, but valence electrons. These are just electrons in the outer shell. If we look at what that would do, we end up getting 2 in the middle from each of them for a double bond. And that's how the Lewis structure would look, and the other way of showing that is just as a double bond here. And that's the only way that we can arrange it so that each of those oxygens ends up having 8 electrons. They have to share a double bond, and that would be what's predicted by the bond order as well.